So, welcome to this episode of Robots in Depth. Today I'm very excited. We are talking modular robotics and the cutting edge of modular robotics. And I'm very happy to have Julien Bourgeois here. And he's going to show us a lot of stuff. But we're going to start where we always start. How did you get into robotics? When did you discover the field that you could build these things and program them?
So I'm a computer scientist originally. So I always been interested in robots and in robotics, but as a leisure thing. And when my former laboratory merged into a bigger structure, the FEMTO-ST Institute, we tried to set up some collaborations between different labs in different domains. And I came up with a project with computer science, distributed computing to be more precise, and robots, micro robots. And then I came up with this idea of building what I call distributed intelligent micro electromechanical systems. Yeah. DMEMS for short. And then I met Seth Goldstein at the University of Carnegie Mellon, and we had the same vision about distributed computing applied to robotics. So I moved to Carnegie Mellon for 1 year on the position of a visiting professor. And then we started to work on this project of programmable matter.
Yeah, and this is so trippy for me because 2005, I read a paper in New Scientist. And if I hadn't picked up that magazine, it was an old one, it wasn't even the one come in the mail today. I just picked it up because it was lying there. I read it and I found the Claytronics project by Seth Copen Goldstein and others, and that's what set me on this journey. I mean, without reading about that, I wouldn't be sitting where I am today. And I'm very happy where I am, I can tell you. And having guys like you talk to me about, and of course you, the audience, about this, and it is just amazing. And you even brought some stuff for us to show. So how old is this project? How long have you been working on it?
For the whole project, I mean...
since the merger then, right?
Yeah, since the merge, it's been like 10 years, I think.
Oh, yeah.
More or less. So it's a long-term project. I think we can't lie and say that it will be ready in 2 years. It won't, but it's a long-term goal and objective because it's a very complex problem with hardware challenges and software challenges as well. So,
and I when he says challenges, he really means it. I mean, he's pretty polite because most of the modular robotics is bloody hard. Pardon my French. I mean, the number of problems we face with this, as you said, in hardware and in software is just mind-boggling. And I think that to have made the progress you have in the first 10 years is amazing. And it's going to take time, it's going to take a lot of effort, and it's going to take monumental breakthroughs, but the reward at the end is also fundamental. I mean, if we get, or I would, and I hope you agree with me, when we get this to work, the world we live in is going to change in a way that is just mind-boggling, right?
I think it will be important to have a matter that we can program, because we have to imagine that every object can be molded into a different shape by itself or by an external computer. So it can really change many things. We can't imagine yet. I mean, we are thinking to applications, but I think it's when we will have the technology that we will be able to see what we can do with it. We can think of deformable screens that can take any shape in 2D or in 3D. We can think also to a kind of training facility for surgeon. You take a MRI and then you can train on a fake body made
that
from
feels real.
Yeah, that feels real.
It's not a virtual reality thing. It's actually there, and it will not only respond to your touch, but it will also move. Right? If you're working on a beating heart, you're going to feel it beat, right?
Yeah, and moreover, you can peel it off. For example, saying, okay, I don't want the skin, and the skin just removed by itself. So it can provide many advantages over the existing technologies. We are also thinking to easier development cycle for complex parts. When you have the CAD software on your computer, you transfer into the matter, you mold it by hand, and then it's transferred back to the computer. So it's interactive computer AD design process.
That's going to be really cool. And what I've been thinking about this area for quite some time, and what I think is that the revolution is also going to be happening on a macro scale, on a large scale, because today we create a lot of things, objects around that we use sometimes, but most of the time it's just waiting, right? I mean, we can talk about the average use time of a power tool in a regular home, and I've heard that it's 14 minutes on its entire lifespan. So we've extracted the resources from the earth, we have put the energy in, and then it just lies there. We even have to build somewhere to store it, and then we use it for 14 minutes over 20 years, and then we throw it away. So with this, we could have what we could call concurrent items. They are there when we want them, but they're not there when we don't want them. Then they are somewhere else being useful for someone else, right? So if you look at energy consumption, if you look at raw material consumption, if you look at logistics, of course, transportation, I mean, we're talking many magnitudes of difference in the impact we will have on the planet we live on, and of course totally depend on.
It could be also self-healing structures.
Yeah.
I mean, when you have some damages done to the structure, you can repair, or the structure can repair by itself. So giving more tolerance to failure, to faults, and because it's also a distributed design, so it can provide more robustness to the object. We are also thinking about what we can do with the space agencies, because on space we would like to have many tools, but
every pound is lots and lots of money.
Exactly. So it's also a possibility of application. And the last one is also having something that can repair by itself. It's also interesting, especially in the space.
Yeah, and I would also say, for instance, in transportation, I mean, if you have a system that could, what we call in computer terms, degrade gracefully. So something breaks. I mean, of course, these units are not perfect. They're going to break. They're going to malfunction. So that happens. But instead of the whole system stopping providing the service it's doing immediately, it can degrade just a tiny little bit. The car is going to go a little slower. It might not have exactly the same handling capabilities, but it's not going to crash, right? Because the other pieces can absorb the slack. The overall solution can reconfigure to still meet most of your needs. And most of our things around us are rarely used to their absolute maximum capacity. So most likely you won't even notice that one is broken. It's just going to automatically order a new one and replace that part. I also think that we throw away so much of our stuff because a small but critical part is broken. Most of whatever we're throwing away is perfectly okay. So there's another venue for waste that we could seriously address with these systems. Because we could go in and in an economical and practical way replace parts, and then of course continue to use most of what we put in there. Can you talk a little bit about the origins of your work in this? You started working with Carnegie Mellon and you based your work on some of what they did, and what did you start with?
So first, before joining Claytronics project, I worked on building production lines for sorting micro objects.
So we're talking really small, below the size of a grain, right?
Yeah, very small objects used, for example, in watches or some kind of stuff. And we made an array of sensors and actuators that can transport parts, but also sort them according to the shape without needing any camera. So everything was embedded into the components. So
was that because the camera is hard at that scale, or was it just because you wanted to make it more simple?
No, first it's hard, and if you have centimeter size conveying belt, you will need maybe many cameras. Cameras are big.
You simply can't fit them tight enough.
So you'll have only partial view of the conveying belt. And
so many interesting problems I get to hear about. You can't fit the cameras tight enough. I never thought about that.
And furthermore, it's better if the production line can do it all by itself.
It's also cheaper, of course.
Yeah. So we finished this project. The technology has been sold to a company, but for bigger size element, wafer for solar panel. And then it's when I met Seth, and we began to work together on this project of Claytronics. And now we are still working together on this. So the idea at the beginning was how we can build these elements, but also how can we program millions of distributed entities. And that's also a very hard problem.
I can imagine.
For example, so for example, if you ask a very simple question, how can I get the center of a huge amount of modular robots? In fact, it's not an easy question. I thought it would be like a 15 minutes search on the internet at the beginning, but it appears not to be. Why? Why is that? It's because you can see all these robots as a graph. So finding the center of a graph, even if it's a big graph, it's easy. You have all the tools that you can find. Except that here it's the graph in itself that has to find its own center. And it completely changes the perspectives and the algorithms. So we can't use traditional algorithms to do that. Except that we want them to be to use scarce resources. And you could say I store all the graph in one node, and this one node performs the computation. But that won't happen.
In practice, it wouldn't work.
Right? Yeah, exactly. So we wanted to have a distributed algorithm to do that, and we had to build it from scratch. So that's the lessons that we have learned so far dealing with programmable matter. It's that each time we want something that appears to be simple in distributed computing, it's not in the context of programmable matter, because we have different kinds of perspective.
Actually, from my years of experience with modular robotics at any scale, there's no such thing as an easy problem. But I also feel that the problems in the other end that are very hard to solve with conventional technologies are easy. So we pay the price upfront by algorithms, hardware, everything being very complicated and being very new to us. I mean, we haven't been working on this for millennia like we have with many other things. But the problem we can address in the other end, like reducing our use of energy and raw materials, and those are already solved. If we get there, or I would again hope that when we get there, we have already solved them. I mean, and it isn't so that we solve those very hard problems like you talk about in space, or we talk about in self-healing systems that will degrade gracefully. We talk about all of these things. We solve them not by adding another complex system on top of an already complex system, making it even more likely to fail. They are solved instantly. The solution is baked into the logic of these modular robotic systems, and that makes me, that's so cool in my mind.
Yeah, we have some pros and some cons about using distributed computing. It's harder to do simple things, but at the end,
it's simple to do hard things.
It's simple to do, for example, fault tolerance or many different kinds of stuff that are harder to do with the central computation. So we have a balance always between distributed computation and centralized computation.
Do you think that there is do we really need to think about the central, or is this a sliding scale? In each time we face a problem, do we place ourselves on this scale, fully distributed, fully central? And do we have to choose, or is it always so that we want to go with the distributed?
I think it's going back and forth. It's really.
Is it a sliding scale or is it a binary thing?
No, it's a sliding scale, depending on the technology and on the needs. Either you distribute or you centralize. Now we are more eager to centralize computation within the clouds because we have a huge computing power.
Yeah, but because these don't have a huge amount of computing power.
But the clouds in itself is also a distributed technology. So so we have centralized and distribution at every scale, I think, also.
And maybe we could have our own, a module that is placed somewhere in a structure has its neighbors. And although we can't communicate over the whole solution, a module could theoretically say to the module next to it and say, could you help me with this computation? I'm not strong enough. And since they are close to each other, the communication overhead would be reduced, right? So they could form their own ad hoc cloud with their neighbors, right?
Yeah, so mainly what they are doing is that they are communicating, exchanging data and working together. So that's very important. By themselves, they are useless. I mean, if you take one single unit, it can't do something very useful.
No.
It's when you put all of them together that they can perform computation and also move and do interesting things.
Yeah.
So by essence, programmable matter is a distributed structure.
Yeah. So we talked a bit about how this came about. Now you can show us some hardware here. You have to hold them up pretty high, I think. But,
Yeah.
could we, the two really small ones, I'm thinking going to be challenging. I think we have to cut them in from some external source because they are, I kid you not, they're half this grain of rice is still too big, I would presume. But I've seen them and it's just amazing. But you have two slightly larger mock-ups with you here. Yeah. Maybe we could have a look at those?
Yeah. So I made a bigger scale for you.
Yeah.
So this is what we would like to achieve. It's a quasi-spherical structure. It's not an easy geometry. We worked on the geometry for like 1 year because we wanted to have a quasi-spherical structure, but it's very hard to build it from a sheet of silicium. So we have designed this structure so that it can be built.
Very important. It's pointless
from a flat surface.
Yeah.
So first, and second, we tried to minimize the force, the strength, the power used for moving.
Roll it because they are supposed to roll over each other.
Yeah, they are supposed to roll like that.
Okay.
With each other.
Yeah.
So
using what kind of force? Is it magnetic or is it electrostatic?
Electrostatic.
Okay. So it's then controllable on and off, so to speak.
Yeah. So we have two kinds of actuators. The bigger square here are latching actuators.
Okay.
And on the other face, it's moving actuators, such that we can make.
So you can move over with a weaker and more basic one, but you can latch at other points, right?
Exactly. Yeah. So it's a bigger scale unit. So we are now trying to design them for being 1 centimeter diameter size.
That's amazing.
It's University of Tokyo who is in charge of building the robot, the shell, and the actuation.
Yeah.
And the processing unit will be integrated.
Yeah, and I can tell you guys, this is absolutely tiny. If you hold it up to camera there, there's 2 lines of text, and then there's a small dot. That's the computer. I mean, we're talking not pocket sized. We're talking, that's. So and this is, as I understand, reasonably powerful. This isn't a kind of a super small computer. It's a decent computer, right?
Yeah, it's a decent computer. It's a ARM Cortex M0.
Yeah.
It's developed by the team of David Blow at University of Michigan, and it's already commercialized. I mean, if you want to buy some, it's commercialized by CubeWorks.
CubeWorks, yeah, we'll be happy to call them out because I mean, this is amazing stuff they're doing.
So they have
that's a grain of rice sized computer, right?
They have 3 sizes of these.
And this one is the size.
It's the smallest.
Ah, okay. I'm thinking the other one is going to be big, but not very big, right?
No, and it's in fact it's too big still. So
it's still you still need to shrink it.
Yeah.
Well, you have some demands. You're not satisfied easily, right?
Yeah. Why is that? It's because if you imagine this sphere flat, we will plug these elements on the flat surfaces that are here, but it means that it's like 2 millimeters long, a bit less, but and if you put 1 chip on a flat surface, the total size will be 1 centimeter, and we would like to shrink it. We'd like to go below the centimeter. We would like to reach millimeter scales. So we'll need to find a way to do it, but it will be for future works.
Yeah, if somebody out there has probably, most of you have probably heard about the big hairy problem. This guy's selected a big hairy problem, I can say, because if your 2 millimeter square computer is too big, you know you're working on something that's challenging. That's amazing. So have you thought any about of application? I would presume that this is very, very early, right? I mean, you're just working towards something that is working. So application is very far away, I would presume. Huh?
Yeah. It's not.
It's decades, right?
Yeah, it's in the decades. So.
Yeah. But that's also. Can you imagine where we are today? We are where people discovered electricity and then they didn't know anything about it and everything was really hard, and then Maxwell comes along and Faraday and all the other guys comes and do this enormous work, and we have the opportunity to be a part of that in some respect, and that's just amazing. Yeah?
So the applications are not for next year, but we have some industrial partners like the PSA group, the car maker, Peugeot, Citroën, so it's a French car maker. So they are aware that it's not a project for the next year.
But there is the group, I can say. I mean, those companies he mentioned, they more or less made the car. They're 125 years old in that business. So. But they're used to long-term projects, right?
Exactly, but there are partners in the project. We also have Tech Powers Electronics. It's a French also company. So we have some industrial partners for this project. So we can feel that there is an interest from companies.
Yeah, and I also think that you mentioned niche and niches with very special needs, like for instance space. Where cost per item is more or less irrelevant because all the costs around are so huge, most costs is drown, right? And I think that they're the properties that we can offer that makes modular robotics so special. Self-healing, I'm sure the guys running Hubble would have loved self-healing instead of sending up the space shuttle to fix everything.
Sure.
And I mean, whatever they paid for the self-healing system would have been a round-off error sending up that rescue mission. Yeah, and of course, when we send things deeper into space, we simply more or less can't get there, right? I mean, although we theoretically could go there, it's practically impossible. And we send out billions and billions and billions into space and just hope they work. And that kind of makes you nervous, I would presume. So those will have the need, and they'll simply, when you become just marginally available, they will be a customer, of course, and then of course we can build from there, right?
Yeah, probably, because at the beginning the cost will be quite high, because it's a batch fabrication. It could be a batch fabrication process.
Yes, yes.
So that's cool, because the cost will decrease.
Yes,
in terms of the number, but. The problem is to reach the
Yes.
huge number of elements. It's like a microprocessor.
Yeah. If we made microprocessors
Yeah,
one by one, a computer would be trillions of
Yeah,
dollars.
yeah, exactly. The design costs
Yeah.
millions of dollars.
We don't even do supercomputers that way anymore. They use off-the-shelf graphic cards, right? So I
Yeah,
mean,
yeah.
yeah. And what I think about production of these, which is also a bit trippy for an engineer, because of course there's kind of two modes of production. First, we have to make the physical unit, right? And then we make from the unit, we assemble whatever we need in the second stage. But are you aiming for a totally homogeneous system with only one type of module, or are you going for where there is a number of different modules cooperating, or how are you looking at that?
So for now, we are focusing on homogeneous modules.
So one type of module then?
Yeah, exactly, because it's easier to design. However, having two kinds of modules can be interesting for different functionalities. For example, we are right now studying the mechanical properties of the ensemble. And if you look at the concrete, for example, it is composed of small elements and bigger size elements, and it's all together that is forming something that is very hard. So maybe we would need some heterogeneity, having bigger size modules and smaller size, depending on the applications. But for now, we have enough work with only building the same module. So
yeah, I understand fully. What I also think about this when it comes to production is that we produce a very small set of units, and I'm coming back to this environmental thing all the time, because of course that's one of the major global macro issues we're facing today, and we have a challenging time really addressing it. It is that we build one factory making modules, if it's one type or maybe 10 types. I've heard 1,000 types could do more or less anything. We could also build the reverse factory. So not only are we environmentally friendly in the sense that we could build things and rebuild things with using basically only energy and very small amounts of it compared to kind of melting the metal and doing a new thing. But we could also, since we have so few types and we know them perfectly, we could actually build a reverse factory, pick it apart, replace worn components and reuse okay components. And when we get the worn components in, we have solved the holy grail of recycling. We know exactly what material it is. So we can say that this is exactly the alloy of metal, this is exactly the plastic we're using, and that means that the recycling material we get out of this when a component is actually worn out or too damaged to use, we can recycle them with a much better result than we do today. I've heard people saying that it will be for metals, it will be a one-to-one. So we put one component in, we use it, we get the material out, and the material is of the same specification as we got it from the mine. There's no degradation. You could go through that more or less endless amounts of cycles, and the material would be as useful for us after those cycles as before those cycles. So that means we could recycle materials for millennia rather than for, like plastic, for instance. When we get recycled plastic, it basically goes into garbage bags and other things of low quality, of low value, because we can't separate the different plastics. Metal goes into counterweights or rebar, but it is degraded. Here we can even address such a fundamental issue, and I just think that it's amazingly cool.
Yeah, we didn't think about that, but it's a very interesting point of view.
Yeah, I've been thinking about this for 13 years by now. So yeah, and every time I know, completely blows my mind. I mean, I know it's an overused term, but this is crack for engineers, though. You can just build anything. And I think also, I would love to have a piece of art made out of this. The technical specification will be pretty lax, but if I could have 20 of those round modules constantly rebuilding themselves, and I know that I'd never see the same piece of art twice. That would be amazing. I'd buy that in a heartbeat.
So you're right to talk about arts, because we obtain a European project, part of a European project about that. We have 2 artists in residence.
See, I love modular robotics. It's the science with artists in residence. I love that.
So the artists are called Senocosm, and they are now working on some art exhibition using programmable materials. So as we don't have the small scale robots, they will use the Blinky blocks that have been designed first at Carnegie Mellon University and that we have now industrialized to create art exhibition using modular structure and computation. So all together. So they have all already worked on this, and we have quite some interesting results. What we can do with that is we can play sounds, display lights, so they can glow in different colors, and we can interact with them. I mean, the public will be able to interact. For example, you can touch them. We have a gyroscope and also a microphone, so you can talk to them.
And when you tap it, the microphone will also be able to hear that.
Exactly, so either way. But they will also sense the...
okay. What kind of sensor do you have? Except you have the microphone and the gyro?
Yeah, IMU, and that's it. Microphone, IMU are the sensors. And actuators are speaker and LED...
that glows. Yeah, but that's amazing. That's so cool. And if we look at it from that perspective, art is also not that price sensitive a market, right? Because some people pay a lot for works of art, and I mean, lots of people have a painting at home, but very few people have a modular robotic self-reconfiguring sculpture, right? You're gonna be the first art collector to have one of those in your collection.
Exactly.
Yeah, so this is amazing.
So we plan to have an exhibition by the end of this year.
Where?
The first exhibition. We don't know yet. We will produce the artwork and then finding the place.
Yeah, and I'll share that on my blog flexibilityenvelope.com, and I will also love to bring it to Stockholm here and to show it here. Because
but it was very funny because we had a presentation at Centre Pompidou in Paris, and they have an exhibition about computer science and all this stuff, and they showed us a work from Simon Fraser, who is an architect, and he has designed exactly this kind of structure like 30 years ago. Bigger size, not really working, and nobody understood what he wanted to build.
So that was Simon Fraser?
Yes.
Was he affiliated with a school or a company or something so people can find him?
University of Cambridge.
University of Cambridge. I'm going to look that guy up. And I know there is a number of architects that have been looking at larger structures like houses and buildings. And all the way back to Jules Verne talked about this, where he thought about a city you would rebuild every year to make it fresh and to adapt it.
Rebuild, but also interact.
Yes. I don't think he had the interaction part because I mean this was 1880 something. So,
sure.
But then of course there's other architects that have been thinking about reconfigurable structures, and also structure, as you say, that you can interact with and they can reconfigure based on your interactions. And have you thought any about, we're talking about the smaller scale going down to a centimeter, have you thought anything about larger scale? Can you build me a house with this, or?
Not really.
Do you know anybody working on a larger scale?
No, because there are many projects about modular robots at the larger scale, but the problem is that you need some forces for latching and also for moving. And if you have bigger scale units, it's very hard to combine them both. Either you go for mechanical actuation, but it's very difficult to do it. It's you have many failures due to mechanical structures inside, moving parts and all of this. And if you want to use magnetic forces, electromagnetic forces, they will eat and use lots of power, because to stick you need to power. So. So that's why we are using electrostatics, and that's also why we are building the smallest possible object.
Because it scales that way, right?
Exactly. It's not only a matter of having small objects. It's because we can use electrostatic forces efficiently at this scale.
They improve with this when the size goes down instead of the other way around, right?
Exactly.
Yeah, I know the connector in modular robotics, how to connect things are just ridiculously complicated. I mean, in an area with lots of ridiculously complicated problem, that's a ridiculously complicated problem. I made a list a long time ago, about the requirements that we would like a possible connector to fulfill. And I think I'm at 49 requirements now, or 51 or something like that. Whereas I think 16 are diametrically opposed to each other. So the more you get of one, the less you get of another. And we need maximum of both at the same time. So yeah, I think that's, but coming back to that with the size of the structure, you talked about interacting with them. The larger cubes here, we can touch, we can press, so we could kind of interact with them at that level. The smaller ones, will I be able to touch them? How durable will they be for me to interact with them? Can I build a table out of them and put a dinner plate on it, or do I need to just look at them?
For now, we didn't include any sensors within them, but it could be.
Are they physically strong, the connections, or?
Yeah, the electrostatic forces, when they are in place, they are very strong.
Yeah, okay.
The problem is that if the forces decrease with the square of the distance between the connectors.
So they have to be.
So they have to be, the surfaces in contact have to be very flat. But when I say very flat, it's microns.
Again, a hard problem. A grain of hair would be gargantuan at that level.
Yeah, exactly. When I say flat, it means very, very flat. And we have made some tests with the 1 millimeter scale catome, and it's you break the structure before breaking the connection.
Yeah, I find that very important. This is a thing we in the modular robotics community, if I can call myself out to be a part of that, we talk about should we cling on to broken modules, or should we be able to let them go? And my opinion is that if something goes wrong, we should keep a hold of it, because it's better that we know where it is, or at least parts of where it is, or where parts of it is, and then we can kind of put that in an area where we take care of broken units. Other people talk about unlatching from a broken unit as important, because then the system can go on. But yeah, the number of the amount of precision we need here is just mind-boggling in some way. Because why I want one that I can interact with physically is because then we can start to make structure that people can interact with and use, rather than just watch. I don't say that there isn't a huge market for the other one too, but when we can start to make physical objects that we can interact with, that would be just amazing.
But we have room inside for integrated sensors, and I mean, using the M3 mode from University of Michigan, they have already developed some sensors, so we can include them directly.
What kind of sensors are we already talking about? We have the IMU, we have the microphone, we have the LED.
For these blocks.
Yes, yes.
If we are talking to the small scale, so this one, they have already.
Oh, that's a really hard problem.
Temperature. They have like small cameras.
But with low resolution?
Yeah, low resolution.
But we could probably use, since there's so many of them, we could just use many cameras and kind of build an image.
Yeah, exactly. That's also something we...
Studio 2.0. And a gazillion cameras making a 3D image. Yeah.
So they have different kinds of sensors already. So that can be included directly because they had a clever design of this mode, using some kind of standardized communications between all the modules, such that it's completely changeable. You can use different layers with different functionalities all together.
Very interesting, very interesting. You've been in this field for a while now, and you think about it like I do quite a lot, which is obsessed about it all the time. But I mean, let's call it quite a lot. What has been your major revelations that and that also provides the driving force for working with this for decades? What's your end goal, except that it's a cool problem to work on? Why do you see the big reason for us to work on it, invest money in it, invest resources in it?
For me, the biggest interest is because it's at the conjunction of hardware and software development. When you work on a computer science project, you only have something virtual. When you work on the robotics part, you have the object, but you don't have the full usage of it. It's when you combine both that you can have all the perspectives that are very interesting to show. So,
and also going back again, you talked about doing an initial release, molding it with your hand, putting it back into the computer and iterating that's going to be an awesome thing, right?
Yeah, exactly. I think this is very interesting, this relation between virtual and physical world. I mean, from a philosophic point of view also.
Yeah, the grander scheme of things. Yeah, I think that is one of my rationales for doing this, and I put a lot of effort into this.
Me too.
Yeah, and I think it's the environmental, the durability, the sustainability, but also the ability to do so many new things and put so much more capabilities into the hands of so many more. I mean, today to produce physical items is complicated. You need a big factory, you need lots of money and lots of skill and lots of time, and it's hard to share skills. We've seen the 3D printer revolution just by the fact that you can share modules between each other. But if we made this, or again, when we make it work, this is going to have such a profound effect on so many areas. It's hard to imagine. Yeah. I usually say this is the same thing as the transistor or electricity or magnetism or some of those fundamental discoveries we've been doing over the millennia.
And we even didn't think about what combined functionalities we can provide. For example, maybe all these robots working together can replace the computing power of a phone or another kinds of element. So combining their physical appearance is one thing, but also combining their computational power maybe can provide some new applications or new elements. I think we are really now before the beginning of all of this.
Yeah, and I think that it's an amazing time to be active in the area, and I understand that from a science perspective this is just perfect. Very hard problems that you can sink your teeth in over a long time, but also with a huge end goal, and there's always some traction shown. I mean, we talk about the problems are hard, but we are making progress, and that just keeps me so excited about this area. So thank you very much for taking the time to do an interview. I appreciate that a lot. And this is your first interview, but it's certainly not your last. We're going to follow this area forever, and I think the audience is also going to be excited about seeing the progress. Thank you very much for taking the time.
Thank you so much for this interview. It was very nice to not only to interview, but to talk without you about this subject. We can feel that. I can feel that you have a passion about that.
Yeah, this is something the audience doesn't know, but my job here is to carry the equipment and make the interviewee feel comfortable, and they do the rest. I don't know anything; they know so much more, and I'm very happy that you take the time to share this knowledge with everyone.
It was a pleasure.
Thank you.
Thank you.
I hope you liked this episode of Robots in Depth. I'm proud to produce Robots in Depth with the support of the sponsors, Carbon Robotics and Aptomica. Carbon Robotics is redefining the relationship between humans and machines by making advanced automation dramatically more accessible, with low-cost robotic arms, integrated vision, and a powerful task intelligence engine that automates tasks no human was born to do. Carbon Robotics is proud to support Robots in Depth in their goal to elevate the global robotics ecosystem. Aptomica rents anything in modular robotics. Dream, rent, build. Visit aptomica.com to connect. If you like this episode, tell your friends, give us a thumbs up, subscribe and turn on your notifications. I am Per Sherboy, and I'll see you next week in another episode of Robots in Depth.